We are now recording. Let's get the slideshow set up from the current slide and we'll be ready to go. If it'll come up. There it comes. First I want to know let me give you these other minor announcements because they affect my office hours. Okay. Number one. Tomorrow, most Fridays I'm on Birmingham campus 7:45 to 1. Last Friday I wasn't because I had an infusion. I was at Kirkland Clinic by 6:30 and left there about 4:30. So, no, not on campus at all. Tomorrow, I won't be on campus much at all either. I'll be there at 6 and come back at 6 p.m., okay? We've got a math meetings down in Opelika at Southern Union State Community College, and a group of us are going down there. We're leaving around 6 in the morning. We'll be back about 6 in the evening. So I will not be on campus for any of my office hours tomorrow. Next Friday, I have my annual physical. Sorry about this, 3 in a row, but it starts at 8, so I'll probably be at the clinic by 7:45, which is when I'm usually on Birmingham campus. Won't be there then. Hopefully the physical will be over with by 9. If so, hopefully I'll be back on campus by 9:45 or 10. So we'll see how that goes, but I will be on campus, but it won't be at 7:45. Be closer to probably 10 o'clock, 10 to 1 approximately. All right, any questions on anything we've covered so far? All right, let me also say this, because we are getting awfully close to midterm, okay? This week and next week are the last 2 weeks in the first mini-term. After that, we're at midterm, and then we'll be in the second mini-term. Now, 1 out of 10 have turned in a paper so far. Please don't let too much time go by. Oh, yeah, okay. Miss Grumpy, okay. So, that'll make you even grumpier, right? Now, what's more, exactly half of you have turned in the first test, which is good. So we're getting close to being ready for the second test. Please don't let second test get to you and you still haven't turned in the first. Okay, so get that done. All right. Any questions before we move into where we left off last time? We're on page 313, chapter 4, section 4.6, graphs of other trigonometric functions. And how do we go about graphing? And these are called the reciprocal functions, which I prefer. I mean, they're just secant and cosecant, reciprocals of sine and cosine. How do you graph these? Graph the sine or cosine first. Whichever one is the reciprocal of, graph it first. So, for instance, if you're wanting to graph the cosecant function, don't worry with cosecant yet. Graph the sine for exactly the same parameters. Now, this is set up for the basic sine. Sine starts at 0, goes up to 1, down to 0, down to -1, and goes like this. The period is 2 pi, a quarter of a period is pi halves. Those are key points. Plot those points and draw the sine out. How does that help you do cosecant? First thing it tells you, every place that sine is 0, since cosecant is reciprocal of sine, cosecant's undefined. You can't divide by 0. So everywhere that sine is 0, do a vertical asymptote. They didn't do one here, but it is one. One here, one here. Everywhere that sine is 0, do a vertical asymptote. Okay. Next, because it's reciprocal, the reciprocal of 1 is 1. The reciprocal of -1 is -1. Okay. So all your peaks for the sine is going to be a valley for cosecant. And every valley for sine is going to be a peak for cosecant. So pick those points. And then from these points, just go approach your vertical asymptote. Okay? Remember, cosecant is always greater than or equal to 1 or less than or equal to -1. So if you get the vertical asymptotes in place, get your midpoint in place, and then just go down or go up from there toward the vertical asymptotes is graphed. That's all. That's all you have to do. Now, if you had some other, okay, let's just look at this first. I'll get to the other way. The period, because it's reciprocal of sine, the period of sine is 2 pi, the period of cosecant is also 2 pi. Now, the domain of sine was all real numbers. Not for cosecant, though, because every place where sine is 0, you can't have a cosecant because you can't divide by 0. So sine is 0 every n pi. So all the whole number pi's, or integral pi's, are vertical asymptotes. So those are not included. Now, domain excluding those, that makes them to be the vertical asymptotes. So I don't see why they separate those two. They go hand in glove. What's the range? As I just said, cosecant only goes from +1 to infinity and -1 to negative infinity, or negative infinity to -1. Inclusive at the endpoints, at 1. Of course, infinities aren't endpoints. Symmetric, just like sine is symmetric about the origin, so is cosecant. What you see up here, you see opposite down here. Okay. How do you graph secant? What's its reciprocal function? Cosine. So graph the cosine first. Cosine starts at 1, goes down to 0 at 1/2, pi halves, down to -1, +1, and on and on and on. Okay? First thing you do, see where cosine's 0. Because secant is the reciprocal of cosine. You can't divide by 0, so those become your vertical asymptotes. And those are your half pi's. Okay? You'll notice they're the same vertical asymptotes that you use for tangent. Because tangent was sine over cosine. So anywhere that cosine is 0, vertical asymptote for tangent, vertical asymptote for secant. Same thing with cosecant. It's 1 over sine. Cotangent was cosine over sine, so the vertical asymptotes are the same there. Now the difference is, for tangents and cotangents, you had 1 period between every pair of vertical asymptotes. For secant and cosecant, because it goes both positive and negative, you have 1 period is 2 of those increments, okay? Not each increment. So the period is 2 pi because the period for cosine is 2 pi. Domain, all real numbers x's except your half pi's, because that's where cosine is 0. Therefore, those are your vertical asymptotes, all your half pi's. The range, just like it was for cosecant, from negative infinity to 1, including 1, and then negative 1, and then from positive 1, inclusive, up to positive infinity. And it's symmetric about the y-axis because cosine is the even function, symmetric about the y-axis, so is secant. What you see on the left, you see on the right, you see on the left, everywhere. Okay? Make sense? The same principle for this. Draw in your vertical asymptotes, that's everywhere, or draw your cosine curve, okay? Whatever the cosine function is you're doing, draw it. And once you get it in place, draw your vertical asymptotes wherever the cosine is 0, okay? And then from peak of the cosine, go up for the secant, and from the valley of the cosine, go down, approaching the vertical asymptotes. That's all you do. Pretty simple to draw. So in comparing the graphs of the cosecant and secant functions with those of sine and cosine functions respectively, know that the hills of the sines are the valleys of the cosecants, and vice versa. The hills of the cosecant are the valleys of the sine, and same with secant and cosine. For instance, a hill or maximum point on the sine curve corresponds to a valley or relative minimum on the cosecant curve. A valley or minimum value on the sine curve corresponds to the top of a relative maximum on the cosecant curve. And this is a length of that. All right. Half the class is here. Glad y'all are here. Wish the others were. Okay. Any questions so far? All right. Additionally, the x-intercepts of the sine and cosine functions become vertical asymptotes of cosecant and secant functions. Why do they wait and say it now? I said it right at the very beginning. Anything where x or sine or cosine is 0, it's got to be a vertical asymptote for secant or cosecant. Okay? So let's do number 4. Example 4. Now you notice here, it's not just any old cosecant function. You have at least two other things going on here. So where would you begin? No, we didn't skip some. No, okay. We're in the right place. Okay. Getting a little worried, but okay. Where did we start? Before you plot a cosecant function, what should you plot? The sine, the corresponding sine function. Okay? So that will be y is equal to 2 sine x plus pi fourths. Okay? Now you tell me what these various parameters do. It's the first thing you notice there. The A is equal to 2. What does that tell you? The amplitude for this sine curve, cosecants don't have amplitudes, but sines do. The amplitude is 2. So this tells you the amplitude is 2. Okay? What's the next thing you notice here? Say again? B. What's your B? Say again? 1. Exactly. Your B is equal to 1. So what does that tell you? The coefficient of x is your B, right? What is it? Look. Period. What does that tell you about the period? Two pi. It's 2 pi over 1. Okay? 2 pi over B. So this is 2 pi. Now what do we do once we get that period? Divided by 4. So period divided by 4 is 2 pi divided by 4, which is pi halves. That's going to give you your tick marks for your horizontal axis. What's the next thing you notice? What? C is equal to pi fourths. Now what does C represent? Phase shift or horizontal shift. And what direction would this be shifting? Wrong. Left, right. Okay. All right, yes, to the left. Everything that deals with the x is sort of backwards. So it's a plus pi fourths, so it shifts to the left. Okay. Y is going the right directions, x is going the opposite directions. Okay. But that's going to be pi fourths. Now, amend something I just said. Because we have a phase shift of pi fourths, I'm going to have to do my tick marks in pi fourths, not pi halves. Because I've got to get on the right place to begin. You start with the phase shift. So, sketch a graph. So here we go. All right. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And let's go up at least 2, but go up a few more than that. And down at least 2 more than that. Why did I say at least 2? Your amplitude is 2. Yeah, you're going to have to do that. And then you got to flip. That's why we have to go beyond 2 and minus 2. Absolutely. Okay? Now, each one of the horizontal ticks are going to be pi fourths. They would have been pi halves except your phase shift. You got to have everything covered here. So that would be pi fourths, pi halves, 3/4 pi, pi, 1, 2, 3, 4, 2 pi, 1, 2, 3, 4, 3 pi, negative pi fourths, negative pi halves, negative 3/4 pi, negative pi, 1, 2, 3, negative 2 pi, and that's not a very good looking pi, okay, and 1, 2, 3, can't get the next one on there. All right, now since we're doing a cosecant, we're plotting the sine. Where does it begin? Second? Okay, normally it does, but we got a phase shift. So we're going to shift, which way did we say? Left pi fourths, and normally it starts at 0, so we'll start the 0 there. Okay, now remember our quarter period is pi half. That's where the key points are going to be. So pi halves is 2 of these. 1, 2, and it's gone up to the amplitude, 2. 1, 2, and it goes down to 0. 1, 2, it goes down to minus 2. 1, 2, it goes back to 0. 1, 2, it goes up to plus 2 again. 1, 2, it goes down to 0 again. Okay? In the reverse direction, 1, 2, it goes down to negative 2. 1, 2, it's up to 0. 1, 2, it's up to positive 2. 1, 2, down to 0. 1, 2, down to minus 2. So this is what the sine curve looks like. It's not what we're really, that's pretty lousy, isn't it? That we're really plotting, but that's what we got to get started. Now, what do we do from there? Hint, I'm changing my color to red. Why would I be doing that? Why would I do that? So the first thing I suggest that you plot once you've drawn your sine curve. You're really not interested in the sine curve. You're interested in the cosecant curve. But why did I change the red? Yeah, vertical asymptotes. Got it. Ding, 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 ding. Okay. Chevette is here. If I can find you, there you are. Okay. All right. 3/4 of the class is here. Okay, hopefully they'll keep. No, that's not quite right. Yeah, that's right. No. 3/10 of the class. 3/5 of the class is here. I can't do my math. Okay. So, where do we put our horizontal, vertical asymptotes? Why did we plot the sine curve anywhere? Because I told you to, right? Okay. What benefit do you get from it? What about the sine curve? What do you use about that sine curve to do your vertical asymptotes? Second? I can't hear you.
Half a period.
Okay, yeah, you're right there. Okay, well, where do I put my vertical asymptotes? Yeah, they go vertical. I got it. Okay. All right, good. Okay. How is cosecant related to sine? Reciprocal, right? And what reciprocal means divided by, right? 1 over, right? And what can you never divide by? 0. So you look for the zeros of your sine. That's going to be your vertical asymptotes. And we plotted those in, so let's draw them in. There's a vertical asymptote. There's a vertical asymptote. There's a vertical asymptote. There's a vertical asymptote. Same one, but okay. Vertical asymptote. Vertical asymptote. Vertical asymptote. Vertical asymptote. Another vertical asymptote. Okay, finally. Now, what do we do from here? We know that cosecant curve, and by the way, what color you want your cosecant curve? I've used dark blue and red. Second? Green? Okay. Light or dark? Light? Okay. All right. If I could get it to happen. There it goes. Now, where do we go from here? What other point might you use on the sine curve? Yes, exactly. Your peaks and your valleys. And you know the cosecant goes up from there, down from there, down from here, up from here. All you have to do is make a nice smooth curve. Sound like that guy who teaches art on public radio, don't I? Okay. got it. That's it. Okay? That's really all you need. You really don't use those quarter pies that much. You really only use the half pies, quarter periods. Use the half periods. You do use the quarter periods because you use the zeros here and the max and mins there. Yeah, you use every one. That's it. The green is all we're interested in, but the blue helps us get there, and the red helps restrict the green. So it's really pretty easy to do. Once you got sine and cosine down, you got secant and cosecant down pretty well too. Make sense? Yeah or nay? Yeah, good. All right. So that was example 4. Let me clear my stuff out of the way so you can see how they did it. And they may do it slightly different order, but basically about the same. Begin by sketching the graph of y is equal to sine x plus pi fourths. Okay, from this function, you see the amplitude is 2, the period is 2 pi. At least this time they're doing right to the period. Okay, and then they go back and solve these equations, which is fine, perfectly fine. And that might help you see why it's negative pi fourths and then 7/4 are your first two. But if you locate that first one, then it's 1 period away, which is 2 pi away. So there are your those are the limits on the first period. Then you draw in the sine curve. Okay? It started at, and you see, I don't know why they did their text the way they did. That would be, oh, I guess these are units of 1. That's what those are. Because the things are changing. I don't know, they don't look like it. I don't know how they did their tick marks, but let's see if you did this as a, yeah, that's a quarter pi. Quarter pi, half pi, 3/4 pi, pi, and yeah. Okay, yeah, they did them like I did. They just didn't put all of them in there. Okay, which makes it a little hard to see. So sure enough, you're starting here, and then draw your sine curve going up to 2 and spaced out according to your half pi's. Here's your quarter pi, and then from there you go half pi, another half pi, another half pi, another half pi. Starting here, half pi, half pi, half pi. These are your key points. Get those plotted, get your sine in place, and then everywhere that sine crosses the x-axis, you know you've got a vertical asymptote. Once you got the vertical asymptotes in place, from the valleys of the sine, that's the peak of a cosecant. Peak of a sine is the valley of a cosecant. And the cosecants are always approaching your vertical asymptotes, never touching. And it's not quite a reflection here, but it almost looks like it is. So that's how you go. Really, all the work is in doing the sine and then identifying those vertical asymptotes and going from the peaks and valleys. You got it not. Okay. Because the sine function is 0 at the midpoint and endpoints of this interval, the corresponding cosecant function is undefined there, has vertical asymptotes at those same places the sine had zeros. Now they're saying this, you should have said that at the very beginning before you graphed anything. The graph will be represented by the black curve that we just showed. All right, now before we get to that, let's go back and do example 5. They didn't show 5 on the, whoa, probably need to get back to dark. Okay. Sketching the graph of a secant function. Sketch the graph of y is equal to secant 2x. Y is equal to secant 2x. Okay, not this one, that one. What are the things you note? First thing you do. Say that one more time.
Change it to cosine.
change the cosine. So you're going to first plot y is equal to cosine of 2x. Now what do you note?
Your A.
What is your A? 1. Okay, your A is 1, which means that's the amplitude in this case. Next,
B.
what's your B? 2. What does that reflect?
Period.
What's the period? Pi. 2 pi over B, which is 2, which is pi. And then once we got a period, what do we do? Divide by 4. So we'll divide the period by 4, and this will be pi 4 cent. Those are going to be my horizontal tick marks. No phase shift, anything else, so we'll go from that. Okay, so let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, negative 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and we'll go up 1, 2, 3, 4, down 1, 2, 3, 4. Okay. How do we plot cosine? Where do we begin?
0. No, 1. Negative
Height. Okay.
1.
1. All right. Okay. I thought you were giving me a multiple choice quiz here. Okay. All right. So we're going to start at 1. There's no phase shift. We'll be starting at 1. And where do we go from there? Oh, let me put these in. Pi fourths, pi halves, pi, 1, 2, 3, 4, 2 pi, negative pi fourths, negative pi halves, negative pi, 1, 2, 3, 4, negative 2 pi. Okay, and this is 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Okay. So we start at 0, 1. That's where cosine usually begins. And where do we go from there? Down to 0, down to minus 1, because we're right on our tick marks, the quarter periods. So we just go from there. Just plot them in. Cosines and sines are usually pretty straightforward and easy to do. Going backward, you go down to 0, down to minus 1, up to 0, up to minus 1, down to 0, down to minus 1, up to 0, up to minus 1, down to 0. So, yeah. So that's your cosine curve. You really don't have to draw it in, but it's usually, goodness, this is ugly. Okay. Now what do you do from there? Yes, vertical asymptotes, I usually do them in red. And where do we put the vertical asymptotes? At the zeros, you're absolutely right. I can't get it to take the, there it goes. So everywhere you have a cosines equal to 0, there your secant is undefined, which is a vertical asymptote. Should have put wider spacing here so I wouldn't have as many of these to do. Okay. Now you want it green again or something else? Oops, wrong thing. What color?
Yellow.
Yellow. Are you going to be able to see it? We'll see. All right. Where do you go from here? Your max is immense. And we go from here and go up. Yeah, you can kind of see that. Here you go down. Here you go up. And here you go down. Here you go up. And here you go down. Up and down. Down and up. All right. That yellow graph is the secant of 2x. The 2x is a horizontal squeeze, shrink, okay? Because the 2 is greater than 1, everything that you do with the x's, the reverse of that is a shrink. And there you have it. Vertical asymptotes where your cosines are zeros. Make sense? All right, good deal. All right. We've already done example 4, so let's get that out of here. Now we're going to move on. Be sure you include the P, okay? The damped trigonometric functions, okay? Graphs. What in the world do we mean by this? Now, the book approaches it from the viewpoint of you got a product of two functions, using the properties of those two functions. For instance, if you had a function f of x is equal to x times the sine of x, you got two functions here. Say g of x equal to x, h of x equals sine x. The product of those two give you f, okay? So you're going to have features of both of those functions in it. And that's a good way to look at it. Y is equal to x, y is equal to sine x, using both of those. Now, I find it a little easier to see and understand and go with if I think of the x as being an amplitude. But now it's not a numeric amplitude, it's a functional amplitude, or it's a variable amplitude. And to me, that's an easier way to look at it. But either way you want to go is fine. So using the properties of absolute value and the fact that the absolute value of sine x is always less than or equal to 1, and of course, absolute value is always greater than or equal to 0 because it's never negative. So you could have put a 0 here. They didn't. I wish they had. That would have made the next statement make a little more sense if they had put 0 is less than or equal to that, because that's obviously true. Now what we do is multiply absolute value of x by all three sides of that inequality. This stays 0, this becomes x sine x, and that becomes absolute value of x, right? Well, that then says that these are the limits of this, okay? Well, 0 is 0. Absolute value of x is the main diagonal. Reflected is also the anti-diagonal. And that becomes the bracket or the envelope in which you put x sine x. Okay? You have a little bit other stuff to worry with, but not too much. Now that's one way of looking at it. The other way of looking at it is x is your variable amplitude. To me, that makes as much sense. Okay? So consequently, if you remove the absolute value signs of this one, then this is going from minus x, that's always less than or equal to x sine x, which is what you got here, and that's always less than or equal to x. Okay? That's what they did here. Now the only thing is they only removed the absolute value size from the inside. They didn't on the outside, because you want x to be always, the thing over here always be negative, the thing over there always positive, so you absolute value of x minus of that, just to keep it in the right perspective. That means the graph of f of x equal x sine x always lies between the lines y is equal to minus x and y is equal to positive x. That's what that tells you. In other words, your plus or minus x becomes your variable amplitude. That's the way I look at it. Okay? So f of x is equal to plus or minus x any time that sine is plus or minus 1. And where is sine plus or minus 1? At your half pies, right? Plus 1 minus 1. is equal to 0 anytime x is your whole pi. Okay? And that's where n is any integer. The graph of f touches the line y is equal to minus x or y is equal to minus x at your half pi's. Has intercepts, x-intercepts at your n pi's, your whole number of pi's. Okay. A sketch of f, the one we were just talking about, is shown here. Now, the one other little feature here that you have to be aware of, okay? Because x is what kind of function, even or odd? Odd. Sine x is odd. And odd times odd is kind of like minus 1 minus gives you a plus. So it gives you an even function. So what you do over here on this side, you do the same on this side. And why is that? When x is negative, so when x is small negative, sine of minus x is also small negative, so the product is small positive. For that first loop, it's up. So basically what you do here, you do your x-axis according to the sine function. And here is Jasmine. All right, we're just missing James, Aaliyah, and Kamari. Okay. All right. So here's how I would proceed on this. Start with your x-axis, plot out the things here. What's the things to note here of sine x? Don't worry about the a, that's going to be a variable amplitude, so don't worry about that yet. But you do the b here, that gives you your period. What would the period be? Second? The b is 1, that makes the period 2 pi. So it's going to start here and repeat itself right over here. Not exactly, but sort of. Starts at 0 here, it's going to be 0 there, 0 going up here, 0 going up there. At different rates, but it's still going up. Okay? So then you do your period is 2 pi, divide that by 4, and you got your pi halves. So you're going to have a key point at pi halves, pi, 3/4 pi, 2 pi, 5/4 pi, 3/2 pi, but yeah, keep on going. 5 halves pi. Same thing here. Negative pi halves, negative pi, negative 3/4 pi, negative 2 pi, negative 5/4 pi, or whatever that comes out to be. So every quarter pi, every half pi, you put a tick mark. Okay? Now, before you start plotting the sine though, also plot y is equal to x. There it is right there. And because you're going between these, do y is equal to minus x. That's your variable amplitude. Okay? Now, sine starts at 0, x starts at 0. So obviously you start at 0, you go up at the first quarter period, which is half pi, and there you reach the maximum. That's your variable amplitude. You intersect that line at x equal pi halves. You're back at a 0 at pi, and then you're back at negative x when you get to 3/2 pi. So you're using these lines as a variable amplitude. So the amplitude is getting bigger the further you go out. Okay? And back to 0 at 2 pi, and up here at 5/2 pi, what would that be? Well, 3 pi. Okay. Now, here's where it gets a little tricky. When you start going negative, you have to realize x would be negative, the sine x would also be negative, so this is positive again. Negative times negative is positive to begin with, until you get to negative pi halves here, then you're going to reach your variable amplitude, which is minus x, okay? Then you go down from there at negative pi to a 0 again. At negative 3 halves pi, you're at your minus x. This would be a minus 1, this would be an x, so you're on this curve here, down here at a negative number. And up here at 0 again at 2 pi, and then up at 5 halves pi, you're at your positive x here again. It's y is equal to negative x, but this is negative and that's negative, so it makes it positive. So you flipped everything around here, and this is your variable amplitude. So place out your tick marks just like you did before. Max, 0, min, 0, max, 0, min, 0. From here, again, this way, max 0, min 0, max 0, min 0. So you just have to reverse them in the middle because both of them are negative. Does that make sense? Draw your envelope. Okay, yeah. Let's go back through. Mark your ticks according to the sine function. Okay? Wherever the quarter periods are, mark those off on your horizontal axis. Then draw in your envelope. I call it. It's your variable amplitude. In this case, it's x here and minus x there. Okay? And then locate your points. On the positive side is easy. 0, or intercept 0, a max at pi halves, an intercept at pi, a min at 3 halves pi, 0 again at 2 pi, a max at 5 quarters pi, a 0 again at 3 pi, and keep on going. On the back side, on the negative side, you note that negative times negative is positive, so this is going to be going up to a max at half a pi, 0 at whole pi, a min at 3 halves pi, a 0 at 2 pi, minus 2 pi, max 0, min. So determine your horizontal scale, draw your envelope is what I call it, your variable amplitudes, and then plot your points. Being careful of the signs, S-I-G-N, that you're going in the right direction, and then from there on, it's connecting the dots. Okay. Any questions? X is called the damping factor. Okay? Be sure you put the P in there. Okay. Let's do example 6. F of x is equal to e to the minus x sine 3x. All right. You got a couple of things to do here. Where do you want to begin? Where do you want to begin? Say again? Okay, let's start with the sine 3x. What does that tell you? Don't worry about amplitude. That's going to be a variable amplitude. So forget that. Okay? You go next to b. What's your b? 3. What does that tell you? It's 2 pi over 3. Is that what you said? 2 pi over 3. Can't reduce that, so we're going to be stuck with it. All right? What that tells me is where to begin, what to put on my horizontal axis. Okay? First, I'm just going to make my tick marks. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now, I'm going to make my verticals too. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5. Okay, got that. Once you got your tick mark, oh yeah, let's go on and label them. This is 2 pi, oh wait. What was I supposed to do once I got my period? Divide by 4. And when you divide this by 4, 2 will go into 4 twice, so you got pi 6. So our tick marks here are at your 6 pi's, pi 6th. Because that gives you your interval, your period, you divide the 4, that gives you max, mins, and intercepts. Okay? Just like we did before. Normal sign would be 2 pi, and we put you start at 0, at pi half, you divide 2 pi by 4, you get pi halves. You have a max. At pi, you have a 0 again. 3/4 of that period, you have a 0, min, and then you're back at 0 again. They all divide up into quarters, okay? Except even tangent and cotangent do. So this gives you pi 6. That'll be pi 6. This will be pi thirds. This will be pi halves. 2/3 pi. And pi. Right. That's all I'm going to get on there. Minus pi 6, minus pi thirds, minus pi halves. 1, 2, 3. I could do minus 2/3 pi. And 1, 2, 3, 1, 2, 3, minus pi. Okay. Leave those alone for now. All right, but remember we're dealing with sign. Okay, those are going to be our tick marks for sign. Next, we got to do the envelope. E to the minus x. Does anyone know how that looks? Or at least give me a few points to plot. Anyone? How does e to the minus x look? At least approximately. Say again? Okay. Let's start with easy. What happens if x equals 0? Say again? What happens when x equals 0 to the e to the minus x? Say again? 1. Absolutely. So let's let that be 1. And how about when x equals 1? What is e approximately? 2.7. Approximately. Which is pretty close to 3. So let's do e to the minus 1 would be close to 3 to the minus 1, which would be close to 1/3. All right. Now, here's another estimate here. What x on our graph here is close to 1? Which of those I plotted there is close to 1? What is pi? What is pi? Y'all all know pi, don't you? 3.14. So that's close to 3. So 1 would be close to pi thirds, wouldn't it? Okay. So when you're close to pi thirds, then your e to the minus x is close to 1/3. Okay? So there's going to be another point if I can get it to draw. Okay? Let's go backward. If x is minus 1, you have e to the minus 1, which would be e to the first. So what would that be? Close to, what did I say e was? 2.7, okay? And minus pi thirds is going to be close to minus 1, so you're going to be up there, okay? If you went out to x equal 2, that would be e to the minus 2, which is almost 3 to the minus 2. That would be about 1/9. So out here, you'd be close to 1/9. Back here, you would be close to 9. 3, 4, 5, 6. It's off scale already. So basically, you've got a curve that comes down like this, right? That's your e to the minus x. Everybody agree? Okay. Now, minus e to the x would just be to reflect that across the x-axis. Okay? So that one would be something like this. All right. There you got your envelope, your variable amplitude. Okay? Now we go back to the sine curve. Okay? Sine of 0 is 0, right? Sine of your first tick mark would be at your max, which would be right here on the curve. Your next tick mark would be a 0 again. The next tick mark would be your min. The next 0 again. And then after that, it gets small really quickly. Going backwards, you started here, you went down. Oh, e to the minus x. Always positive. So the signs, SIGN, for your sign, that follows exactly what it is. So back here, it's going to be a minimum, then a 0, then a maximum, then a 0, and then it's off scale. Okay? So basic your function does something like this. Variable amplitude, whoops, missed it. All right. Whoa, where did my curve go? Okay. Something like that. Your e to the minus x is your damping factor. It's blowing up on the left and squeezing down on the right. And every one of your tick marks, you go a 0, a max, a 0, a min, a 0, a max, a 0, a min, a 0, a max, a 0, a min. You go all like that till the cows come home. After a while, it's just so close to 0 you can't tell what's going on. But this is what's happening. Does that kind of make sense? Set up your x-axis according to the sine curve. It could be a cosine curve too, whichever. Set up your envelope or your variable amplitude according to the first curve, okay? The first function. Draw it for the positive and draw it for the negative, because you've got to stay in between the two. And then using your sign, it's 0, max, 0, min, 0, max, 0, min. Down here it's so close you can't tell. Going backwards, 0, min, 0, max, 0, min. That min's way down there. And then it would be another 0 here. So it'd be coming back up here from somewhere down there and going somewhere way up there. Okay. See how it works? No. Where did I lose you? Do your horizontal tick marks according to the sine or cosine curve. Okay? Do your variable amplitude according to the other curve. In this case, it's e to the minus x. Draw in e to the minus x and then minus e to the minus x. Just reflect that across the x-axis. And then you draw in your sign as if you're going between plus or minus 1, but you're going between plus and minus e to the minus x. That's your variable amplitude. So since it starts at 0, at the first tick mark is at its max, the second tick mark is 0, third is a min, next is a max, next is, a 0, next is a max. By here you can't tell what it's doing. Okay? Going backwards from the 0, you go to a min, up to a 0, up to a max, down to a 0, down to a min, up to a 0, up to a max, and on. set your horizontal axis according to your sine or cosine curve, and then draw your variable amplitude, which is your first function, and then do the opposite of that, give the bottom part of the envelope, and from there you're done. What's that?
Over to the left, when you go up and down to the max and the min,
Right.
there's the positive 3 and negative 3.
No. Wait. Are you using the 3 from here? That's your period. That determines your period. That's what you set up your tick marks here for. Okay? No. You're going up to this curve is a max and minus that curve is a min. So you see this becomes like a variable amplitude. Wherever this curve is, that's your max here. Wherever that one is a min there, a max somewhere way up there. And this is the min here, max, min, max, min. Over here, it just squeezes down really quickly. Here, it expands upward really quickly.
Okay, so, but that's where I'm lost because I just don't know how you know what the max and min is for that.
It just is wherever at this tick mark that is determined by the 3x there. At that tick mark, you know you got to be at a min, so you just keep going down until you hit that curve wherever that is. And this max is wherever that one is. Yeah. Now drawing them. Oh, I know where you got the 3. Okay. Because E is approximately 3. So this E to the minus 1 would be 1/3. Let's see. Yeah. That would be here. And E to the minus 1, when x is 1, that's close to 5/3. I just had to do that to figure out how to do it. Before, the scales haven't mattered. I put the horizontal scale and did that, and vertical scale this. Now we've got sort of a problem because this depends on this scale. And I can plot my sine according to quarter periods, okay? But then I have to plot the E by the actual value of that. So that's where I took the 3. Pi thirds is about 1, and E to the minus 1 is about 1/3. Okay, so that's where that came into be. Okay, and E to the minus 1 would be close to 3, 2.7, and then the next one would have been close to 9, and we didn't get up high enough. We didn't have 9 on the scale here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 would have been up here somewhere. Okay. But I was just using that to approximate, because what you use here usually has a pi in it, and you're not used to using that as a pi. Now, if you got a calculator, yeah, you can calculate that exactly at these points. And that would be what I would do if I had a calculator. I would have done it. But I was just approximating it here. Okay, good question. All right, let me erase my mess and see how they messed up. I mean, how they did it. Okay. And now they go through a lot of things. Consider f of x as a product of 2 functions. Yeah. Okay. Each of which has a set of real numbers as a domain. Yeah. Okay. For any real number x, you know that e to the minus x is always positive. Now that's something we did note. And sine of the absolute value of sine 3x is always plus or minus, is less than 1. Okay. So e to the minus 3x, e to the minus x times the absolute value of sine 3x is less than or equal to e to the minus x. They just took this statement here and multiply e to the minus x times here and e to the minus x there. And then what that meant is that you put minus e to the minus x on this side. That's where the negative of that function came from. So this function has to be always between minus the envelope on the top and minus the envelope on the bottom. Okay? Furthermore, because that stays between plus or minus e to the minus x. And that will be, and by the way, a weird way of saying it, but what we did at the very beginning was find out our quarter periods were pi 6. And then from there on you just do thing, you know, those are the places where you're going to have your maxes and the mins, okay? At the pi 6 plus half of those every time, you know, 2 of those every time, because the first max is at pi 6, and then 2 pi 6 later, which is pi thirds later, and 2 pi 6 later, and 2 pi 6 later. That's how the max min, because in between you got zeros. That's a weird way of saying that, but if you just plot them out there, it makes a lot more sense. Okay? So, see, your zeros are going to be at those half periods. And your period was, I don't remember, period was pi thirds. Yeah. So, 2 pi over 3, yeah. So, yeah, the period was 2 pi over 3, so half a period was pi over 3. So all of those, that are your zeros. So much harder to do it by the equations than it is just to plot them. If you plot out the tick marks, then you see where the half periods, the zeros, the max and mins are. It's a lot easier to do that way than this way, I think. And here's what theirs look like. Now remember, we did our pi 6, which is our quarter period. There's 1 pi 6, 2 pi 6, 3 pi 6, 4 pi 6, 5 pi 6, 6 pi 6, 7 pi 6. It gets to negative pi 6, negative pi thirds, negative, what would that be? Pi halves, yeah, down like this. You've got your E curve in here and minus E to the minus X here, and your sine goes up, down, up, down, up, down, up, or backwards, min, 0, max, 0, min, 0, max, 0, max somewhere else. Just like mine did, only maybe a little prettier. Make sense? They didn't do the actual values here, but if you'll notice here, this one right here at negative pi thirds, this is real close to the 2.7. Okay, and down here it's close to 1/3. Okay. Yeah, it can't be, can it? All right. The next slide will start here. We almost finished 4.6 today. We're going to start at the top of page 316. I already got a mark there. Homework exercises I would do all of 9 through 14. Only the odds have the answers in the book, so check those. Then do any of the odds 15 to 37, any of the odds 39 to 47, any of the odds 49 to 55, any of the odds 57 to 63, any of the odds either 65 or 67, either 69 or 71 or both if you choose, 73 or 75 or both, any of the odds 77 to 81, and then there's a meteorology function, 83, or a distance application 85. Okay, there's exploration, but then they come back to, well, they didn't do many damped functions, did they? So we'll figure it from there. So you can leave off the application. We'll get to those later. Good deal. Have a good weekend. We'll see you Tuesday. That should wake people up.